Okay, so to begin, we will have one of the world leaders of space missions behind Planck, François Bouchet, kick the event off.
So I thought that I guess my job is to sort of set up the basis for the future by telling you the sort of pretty much the end result of a 25-year effort of which was started essentially. We dreamt of that mission as soon as the Kobe result was out, that it was a discovery. And the dream was, well, let's extract everything there is in the temperature anisotropies. And I think we are finally there. So first of all, Planck, the legacy, and then we just did the release of our so-called legacy release at the COSPAR General Assembly meeting in Pasadena mid-time last year, and that's an edited version of that talk that I'm giving. So map legacy, this is pretty much the basis. We have 9 frequency maps here in intensity, and which are very well calibrated, and these are the ones that we promise to deliver, from which you can extract essentially all the information in the CMB. And these are more sort of doing for polarization what WMAP did for intensity, which is, you know, a great step forward but maybe extracting only 10% of the information. And we will want in the future to really get this very crisp at the same level that has been for temperature. And one of the things that Planck did was to open the window on the high frequency side. Kobe and WMAP had this vision from this part, and we've added the high frequency side, and in particular, discover all the wonders that dust can do for us. Well, this was a joke. So in terms of performances, you don't quite see it, but the sort of 143 gigahertz, which is a center for many CMB experiment, the final RMS of the noise here is 0.5 micro-K degree, which is essentially 30, if you prefer 30 micro-K arc min, and we want to go to the, well, typically 30 times below to be able to do justice to this one. So one of the legacy also is a solar dipole now, which is very well known, and with a precision, which is about 0.025%. In other words, we know how well we move as compared to this referential with 100 meter per second accuracy. And this is certainly a legacy for many experiments that now have a proper calibrator just in front of them. And that was only possible because we know very well about the dipole from the dust, from the galaxy. So I think what we finally got to, which I've been arguing for a very long time, is a pretty detailed simulated set of what could be the residual systematic effects, and that's in the latest. For instance, this is all the residual systematic effects in the E modes, both for the core cosmology channels and the other ones. For the time being, we have about 300 sims of this. As you can sort of see, residual systematics are expected to be very much smaller than the signal and the noise, apart from the place where this has been the most difficult for us, which is, and has been the main progress in the last release, which is at low L, where of course tau lives, and where there this is comparable to the noise. And we may have something post-legacy where we hope to actually do 1,000 of this, which is to allow some even finer use of the data, in particular non-Gaussianity. So what Planck did was to open that part of the window. So this is RMS on say half of the sky. So the very complicated business of the various foreground, in particular on the low frequency side, and then how things look in polarization. And then of course, this is just in terms of frequency space, you can do this as space, and you see this sort of, as soon as you just cut the sky, I mean, we have been happy we as a field, to find that essentially the foregrounds are actually relatively low as compared to the primary signal. And that may be slightly less true for polarization, and certainly not true at all for B modes. So one of the things that came out of all of this is this beautiful, graphically beautiful view of the magnetic field of the galaxy, which is essentially obtained by doing a 90-degree rotation of the polarization field that we are measuring at 350 gigahertz. From this, it became clear that it's not going to be that easy to go after gravitational waves, and we need some dust monitor. And the complexity of the dust will tell how many frequency channel we need at high frequency, and whether we can be happy with what the ground can do, or whether we are doomed if we don't go to space if R is very small. This might be okay if R is in the order of 10⁻², though. So that's pretty much the Planck result regarding the CMB when it smooths at the 5-degree scale, so that you can sort of see both the temperature and the polarization field. But that's of course not all the information there is. You cannot represent it though. So what I've done here is to cut out this and show you a zoom on this, which shows that indeed we have a lot of signal including in polarization, and you can keep doing this. And so that was at the first one was at 5 degrees, so this is 20 arc-minute smoothing. So let's do this again. And so this is at 7 minutes of arc smoothing, and you can look in detail at the structure of the two fields and so on. Of course, as to finish on the map, what has been maybe, to me, the thing that has been maybe emotionally the biggest thing is the first full sky lensing map, which has all the same properties as the first DMR map. 10-degree angular resolution, signal to noise of 1, which is, you can only use statistically, but this is the beginning of an era. And it's very exciting that in the future we'll have a high fidelity and high signal to noise rendition of the dark matter distribution in the universe, and all the things you can do by cross-correlating with optical, well, not optical, but light tracers, baryonic tracers. Now, angular power spectra, that's pretty much the basic measurements that we do when we don't bin at all. So these are the 2018 TT spectrum of Planck. When you bin, this is what you get with error bars now, which is just, and most of them are actually just a dispersion due to the finite number of modes, apart from here where you can sort of see that it starts increasing again. That's where noise starts picking up. And the blue curve is a 6-parameter Lambda CDM fit to it, and these are the residual, and there are 60% of the point on the other side, I mean, below 1 sigma from the mean, so all of this is fine. And this is a cosmic variance limited measurement that is essentially, greater than 1 signal to noise. And that's, as we know, as we actually planned and announced it earlier on, this is enough to extract all of the information in Lambda CDM. Of course, if you have other models, then you might benefit to push this a little bit further. Prediction from Lambda CDM plus the parameters in temperature is the curve here, which describes also very well, as you know, both EE and TE modes, which is also very revealing that we've understood something. And so temperature, polarization, and also the lensing are quite consistent, which I haven't shown yet, within Lambda CDM, and it could have been otherwise. Yes, this is a lensing one, and this is a prediction on the basis of the model. Everything fits. Beautiful. So this is a situation with TT, TE, EE, phi. From all of those, we can be fit with a single 6-parameter model with person-type accuracy, of course, but tau. Now, extensions that we've started, and it's a game that has been ongoing for a very long time, trying to sort of add further description of either primordial physics or checking bases and so on. For all of this, we did, as the volume map did before, where all of these were addressed by Planck and often providing the best available constraint theories of all cosmology or astrophysics. So to give you a little bit how much the field has been progressing, here is a reconstruction of a primordial power spectrum at the end of inflation. And here's COBE, pre-WMAP, WMAP, Planck. You can clearly see with Planck that, NS cannot be equal to 1, and that's at more than 8 sigma level with the latest rendition. So really, we've progressed on NS by, the precision on NS has increased by a factor of 100 since COBE. So that's, And that's not the only number that we've progressed by a factor of 100 in these 25 very fruitful years. Situation, as you know, on tensor component, which is really one of the core of what we're looking after in this, well, one of the core things we want to measure in the future, all the way down to maybe models which are very low values. For now, the best constraints are coming from Planck plus VK15, and they are at the level of 0.06, if I remember. Now, one of the things that the increased number of modes have brought is now we can open the Pandora's box and, for instance, say, well, let's look at NS, but let's not stick to the standard value of 3.04 or whatever for NF and some of nu. Before Planck, I mean, of course, you could always trade the determination of NS for some variation around NF. Now, this is just not possible anymore. I mean, even when so the determination on NS is now resilient to opening to broader model. And of course, we've done this to quite a number of other extensions. It will be boring to go through all of this. This is just more illustrating of the power of CMB. And anyway, so let me keep going. So if we look at the figure of merit, that is by how much we've decreased the parameter space, which is computed with this number, for Lambda, CDM, or broader models, and compared to Kobe in 92, well, where I cheated a little bit, I added the tau from HFI 2018. It set it to 1. So pre-WMAP, we had already improved things by a factor of nearly 10 to the 4 in terms of reducing the allowed parameter space. And you sort of see things, and Planck is the latest rendition, and actually we'll see today that this will keep going. We know how much we can go further by a factor of nearly 10 to the 10 for something like ECO, although we don't know where to put it yet because there is a question mark of when would be a very all-encompassing satellite coming in like CMB Barat. Anyway, the thing is, if anything, our capability of reducing the parameter space and, by the way, discovering failures or the need for addition, of course, has been, if anything, increasing with time, and with a 6 months doubling time of this figure of merit, which is very fast for nearly 26 years. So inflationary scorecard, well, lots of things that we've improved by a factor of 100 over the duration of that experiment. Of course, the thing that hasn't, well, we have this, Planck versus other probes. Well, so Planck points are blue, and essentially all of the points which are, doesn't have too large error bars, which are from listed here, ACT, SPT, polar bear, bicep, and so on, are shown on this plot. It's essentially a story of very consistent across experiment, and I think this is just amazing how well all this, the instrumentalists in this field has worked over these 25 years, ground, space, and so on, to the point of, having great consistency. And this also shows that by now, Planck has measured about, with a single tuners of greater than 1, about 1.5 million modes in temperature, and has essentially completed the job. You can still add a little bit in this. But what is crying for help, E modes, we know about 100,000 of them. We need at least 10 times more. And well, phi, we have measured maybe 3,000. So this is this very coarse map of lensing. And in B modes, we have only tens of modes. So from that naive point of view, the future is completely clear. All these modes are crying to be measured, and we know, and it's easy to show through theory, Fisher matrix, whatever, that there is a lot of information which is pretty crucial, which many fields of astronomy will beg if they could actually get that. And so we just have to do this. How is a big question, which I will leave to this audience afterwards. Now, of course, this was CMB, we want also to compare with other probes. This is BBN, this, as you know, this works. We also have now the fact that there are no more contradiction between the optical depth from direct measurements and CMB by now, which is now these tiny error bars there. This is a time series. And now there is good consistency, as you know, for low redshift probes, both with BAO, where this is amazing, redshift space distortion, supernovae when they are not calibrated at around zero. Weak lensing in DES. So when you put all of this together, this is a plot that I really wanted to make. We have now the linear matter power spectrum at z equals 0 from all of those, and this is a grandiose achievement. And we have all these probes that line up, of course, within the context of a model, because the model decides where the points should be on this plot, aligning on one spectrum over 3 decades of scale. So that's pretty much where we stand today as a field. And we've improved over a lot of parameters. And Planck parameters, as surprising as they may have been initially, now they have remained quite consistent across analysis, and they've crossed quite a significant precision threshold over the course of the analysis. Yes. Now, there are mild tension existing. I say this is all fine when you compare in the sigma 8 omega m plane. There is no tension between Planck and lensing, but if you do a joint analysis of DES with galaxy probes, yes, well, there you can sort of see that there is a tension that appears. So what does it mean? Do we understand as well galaxy distribution and its relationship with cosmology? Well, or is this the beginning of a tension? Well, that's something that the future will have to decide. Now, as you all know, there is a strong tension that has been emerging on the direct measurements, and as you know, both the inverse distance ladder as well as the straight CMB gives value which are of the order of 67 kilometers per second per megaparsec, while the calibration supernovae from with Cepheids and 4 other, tip of the red giant branch, parallaxes from Gaia, all indicate something which is more in this regime. So, well, what does it mean is something that remains to be seen. Initially, a fairly large response of the community would say, oh yeah, that's simple, Planck is wrong, these idiots don't know what they are doing. Then it was found that actually this was quite helpful. It was also found that, in particular, because there you just need RD, and you can get that from WMAP, and that's just, you get the same answer. You can also do it with D over H. So I think it's now pretty much a consensus that this is fairly unlikely to go away by reanalysis or improvement of any of the CMB data. So now which I think leaves us with either there are some systematics we haven't understood at low Z, and when we calibrate directly around us, or that maybe there is the beginning of signs of new physics, which is not that easy to arrange because we need not to destroy the fact that we have great consistency from Lambda LCDM with all different probes, and in particular, you cannot, many explanations that were proposed initially were doing fine, but they ignored polarization, and that was fine because we had been very careful in planning to sort of say, well, I mean, this is not the final say, there are residual systematics, so be careful when you use that. Well, now there is no such excuse. I mean, the polarization is just fine in the legacy release, and so you cannot drop it, and now it make it much harder to find theoretical explanation of why you have all the CMB success, everything fits, while still we have this discrepancy, and in particular the fact that there is this inverse distance ladder is crucial in this discussion. So cosmology post-Planck, or at least today, maybe that's a better way to say it, is Lambda CDM fits all data in temperature, in the E mode, B mode, even though this is less strong for now, phi, and that has been pretty stable across releases. We've decreased uncertainties, increased the control on systematic effects, but we haven't changed pretty much. I mean, we stay straight in our boots pretty much. Lambda CDM, I mean, checks all generic boxes. Temperature and isotropies now have been essentially exhausted, at least primary information has been exhausted. And this is, we essentially delivered at what we promised to ESA at the selection back in 96. After, and I remind that was after 3 years already of study before the selection. But of course, that doesn't mean there is no more information in intensity. There is much to be learned still in foregrounds. We could still improve, say, the power spectrum of SZ, and that will mechanically even further improve the uncertainties on temperature. But of course, I mean, what we are after now is polarization, and this is, this is a future, and there will be lots to be done. But I want to also remind you that a new field has emerged, I mean, CMB lensing, and I think this is with a great scientific potential, and the fact that we're just, now these maps are just from all the stuff that gravitates from now to the light scattering surface is just wonderful. So I think that's, I don't want to conclude on this, only on this triumphant attitude. Yes, of course, we've made a lot of progress, and it's been extremely rewarding to go after the CMB, not only for Planck, for all the community, but there are a lot of open questions that I've listed that other people will address in the course of the day. You pretty much, in this expert audience, know all of them, even though not everybody knows about how to solve this. There is also the point of the so-called curiosities, for instance, sorry, I should finish my sentence. The hemispherical anisotropy, the fact that there is low power around L of 20. So there are all kinds of curiosities, which are all at the level of sub 3 sigma. So just tantalizing, but not enough to tell very much. So there are lots of theory papers, and the only way to go around this is now to have another probe to actually confirm or just decide that this was a statistical fluke. So lots of open questions, and the beauty of it is that we know through a lot of studies that have been done for both to propose and get the funding for ongoing S3 experiment, the science book for S4, the proposal we wrote several times to ESA to do core, which was meant to be all-encompassing. Now this is also being done for CMB Barrett. We know that there is lots of information there that is just waiting, just like it was back in 92. It's obvious we need to do justice to all these modes. So the only question is how fast and well, how we do this instrumentally in detail. And well, you will get to this, and my hope is that India will be part of it, and you can. I did invite one of the gentlemen, one person in India was on the CMB. I invited this gentleman, Tarun, and he participated to the Planck data analysis on the HFI side. Well, let's grow this. So here, I want to conclude on this, and I think I'm pretty much on time.
All right, thanks. That was a great talk. Any questions?
Yeah, so François.
Yes.
Since you brought up the point, this look reminds you of 1990s scientifically. I also thought it would be important for the Indian community to know how it was to build a community in Europe for doing Planck. If you wanted to briefly just mention that.
I'm not sure I got the point. The only thing that the thing that I remember from that time is that, there was these two options that were picked up by the community back in 92. I mean, a group in the US got together and proposed WMAP, a group in Europe, two groups in Europe actually, with US colleagues, by the way, proposed, actually not Planck, it was at the time Cobras and Subha. And we took two different approaches of, one which would be with whatever is available in the lab and do as fast and make the next step, or take a different take and develop the technology to be able to do the full job. We may be seeing a little bit the same thing here between Lightbird and maybe something more ambitious like Pico or something. But, Lightbird is not selected again. I mean, we have to be a little bit careful, but I think clearly at some point we need to, do justice to this gold mine and get all of it, both hemisphere, and of course a very high L will have to be done from the ground. That doesn't make sense to put a 10-meter class telescope in space. the big questions is where is the overlap region between the ground and space? And when is it that we can sort of say, well, yes, foregrounds have been tamed well enough that it can all be done from the ground? Which, of course, depends somewhat on, well, how complex foregrounds are, which remains to be seen. I mean, I think it's, my own opinion on this is that if R turns out to be in the 10⁻² range, I mean, we are pretty well equipped with the information we have and with the capabilities we have and so on. If R turns out to be in the 10⁻³ range, this is really difficult, and the amount of cleaning you have to do on the foreground requires really exquisite precision. And, well, that will require things that may be really challenging to do from the ground. Maybe. Anyway, that was personal for a minute. There can be widely diverging opinion on this. You know, people thought for a while that they could do essentially with very little knowledge of dust. It turned out to be a sour story, but I'm pretty sure the field will avoid doing this again.
I'm going to ask Tarun's question again, maybe in a different way. What are the challenges of growing a community in a field that you're entering? So compare Europe in the 90s as you're thinking about proposing
yes, I got it.
Growing that community.
Got it.
Yeah.
Well, yes, I mean, there is quite a bit of similarity. Actually, India is better equipped in terms of the theory basis than France was when we proposed. I think I was one of the rare guys that had ever written a single paper on CMB when we proposed, which is part of the reason why I had quite of a role in the writing of the initial case when we proposed it to CNES. The thing that has been essential in growing a community has been time, and the fact that there was a beacon, the fact that there was an established program, even though the launch date turned out to be modified, since the initial launch date was 2003, and then there was an Ariane 5 catastrophe and so on, which, so it was delayed, and then so in the end, this was 2009. But anyway, there was quite a bit of time where we could grow the community, where there was, and so from start, we grew everything together, instrumentalists, theorists, and so on, which was very hard in some sense because people have, the time where they can contribute really usefully to the project is a different period of time, and this is on a very long period, so this brings all kinds of questions of reward mechanism and so on, which we can discuss in private. But in the end, the thing that is beautiful is when the community knows that there is a beacon, that there is a program, that it makes sense to take graduate students and so on, and then you can organize meetings. Well, for a very long duration, I organized HFI consortium meeting every other month, and so people are confronted with very good people in the field several times a year, for years in a row. Well, you know, if you have a good basis of students and so on, and a few more senior people, you can grow the community. And we grew that community from, you know, a handful of people to essentially a few hundred people in Europe. I remember the day when we were in the early days where we had, you know, PhD students like Jacques Delabrouille, like Nabila Aghanim, you know, they were all from that time. Well, they grew now in terms of leaders of the field themselves. So that's with time and the decided program, you can do it. And that's, I have absolutely no question. I would even be happy to help. But there is a need for a path. You cannot grow a community without knowing where you are going. I mean, this is suicidal otherwise. I mean, you cannot take young people and just say, well, maybe. So then there are all kinds of other questions. Is it enough to participate to others' experiment? Or do you need some training ground of your own? For us, on HFI, the balloon archaeops played quite a bit of role. We actually The same people that were doing HFI, we did that balloon, and using quite a bit of the same technology, which proved also a technical proving ground, but that also helped to grow the community, to learn how to do the data processing. Not the high end, I mean, not fitting cosmological parameters. I mean, I'm talking about calibrating, taking out glitches, thermal instabilities, and so on. So by the time we got the data, the actual data, we had a very well-trained community already. And by the way, one of the things that I'm very happy I succeeded in doing was I sold to the agency the fact that we needed to have a full-blown ground segment capable of fully processing the data before launch. With the idea that was behind that, then we cope with the unexpected. And indeed, we were able to do the first maps within days of getting the data. And we've spent the following, I don't know how many years, coping with the unexpected, which in our case were glitches, ADC nonlinearity, and a few more.
And thank François for the excellent talk.